Alright, so this is exciting. I just finally, after over a year, set my OBS studio settings to proper settings so I could actually record real, true HD videos now. I don't know what I was doing before, but I always wondered why my videos weren't recording super crisp. Luckily, though, most of the time I had giant text in my videos, so it didn't really matter. But for this program here, as you can see, we have pretty small text. So welcome to the new binary adventure recording settings. So what we're going to cover today is what is disassembly. If you've done any reverse engineering, or you've heard about reverse engineering, or you've done any significant programming in general, you've probably heard of something called a disassembler and disassembly, and also assembly language. So what I want to do in this video is I'm going to show you from the very ground up what all is going on, what a disassembler like Binary Ninja, IDA Pro, Hopper, or even like GDB disassembler is really doing. And once you have that understanding, the power and the awesomeness of those programs will really come to light. And then you'll be able to start manipulating bytes like you've never been able to before. And so what I have here, by the way, this program is called 010 Editor, and it's just a hex editor, okay? So there's another one called HXD. I'm going to put the link for that in the description. I'll put the link for this in the description, and other relevant links in the description. So what we have here is I opened up this exec file, which is actually python.exec. So this is the Python program. So if you're going to do some, or the Python interpreter. And I mean, this could be any what they call PE file or executable Windows file that you could do this with. And the thing that sets 010 Editor apart from the other hex editors is it has this thing called binary templates. And we're about to use that, and we're going to look at exactly all of what's going on here. But if you were to open this file up in a more basic hex editor, I'm going to see if I can do that for you real quick. Let's see. I want to see if I can show you in HXD real quick. So I'm just going to go to the actual directory, which is CPython 27 python.exec. Okay, so CPython 27, and then python.exec. So we're looking at this file right here. So I'm going to drag this onto HXD, and this is the actual executable file, all of it right here. So what's cool about this is you can literally see that it's just a bunch of bytes. So every single one of these two-digit numbers, like 4D, 5A, 90, 00, 03, 00, 00, each one of these is 1 byte, and 1 byte is 8 bits. The first digit stands for the first 4 bits. The second digit stands for the last 4 bits, basically. There's something called endianness, which switches the bytes order, basically. But for the purpose of what you're learning right now, just know that each one of these little groupings is 1 byte, okay? This is machine language right here, to put it bluntly. You hear about machine code, machine language, and everybody knows that this is like binary. So basically what ends up happening is when the computer actually is looking at these numbers, it's going to see 4D as this right here, 01, 00, 11, 01. And then it's going to go, to the next byte, and it's going to see 5A as 0101, 1010. So you can see that like 5A is that number. They're not two different numbers, it's the same number. The only difference is 5A is in hexadecimal, so the base is changed. And short answer, the reason why we do that is because hexadecimal works nicely with binary, and it allows us to write these longer numbers in less space. So, and they're also more readable because these are more distinguishable than just a whole bunch of ones and zeros. So that's the short on that. Now, the question may become then, how does the computer make sense of all this? it's just a whole bunch of numbers, but obviously the computer has to make sense of it, and the loader, when the operating system loads the file up. And so basically in this file is data in the form of bytes, instructions in the form of bytes, and that's basically it. Everything's either data or instructions, and ultimately even instructions are data. And so what we have here is we have basically the computer, the way that it is able to figure this stuff out is done by interpretation. So some of these bytes in here will be interpreted as just information that can be acted upon, while other bytes may be interpreted as actual instructions. And that's all I'm going to show you in this HXD for right now. Let me see if I can. I'm just trying to see if I can actually zoom in here. I don't know how to do it. I don't even know if you can do it. But anyway, so that's what I'm going to show you here. Now I'm going to go back over to what I consider to be a more awesome hex editor here. And basically, each executable file on Windows, which is referred to as a PE file or a portable executable, which also includes DLL files, by the way, has what they call a header. Actually, it has several headers. And all these headers are data structures. It would be really helpful if you don't understand what a C struct is to go and learn about what a C struct is at this point in time. But long story short, a C struct is just, I'll show you in, actually, you know what? I'm going to show you in Vim. A C struct, like this, is just several variables that will be grouped together, or several other pieces of data that will be grouped together. So it could be int age, char name 50, and int height in inches. Okay, so all this is it's just a group of sequential bytes that will be interpreted as various pieces of information. So, for example, an integer might be 4 bytes. So we have 4 bytes here, and then every single char is 1 byte. We have 50 chars. We have 50 bytes here, and then we have another 4 bytes. So in total here, we're working with 54 bytes in this struct. Now, the struct itself may end up taking more space than that because there's something called padding and alignment where the operating system tries to make things aligned on certain numbers of bytes so that it can better and more easily work with data. But you don't have to worry about that right now. So what you really need to know here is that we have 58 bytes in this struct. So let's say this struct is called struct person. Okay, let's say it's called struct person. So every single time we use struct person and we create a variable of type struct person, the program and the operating system will create space for this many variables, and they will be pretty much in sequential order next to each other, adjacent to each other. Sort of like an array in a programming language as well. If you create an int array of 50, it's going to create 50 times 4 bytes. So it's going to end up using 200 bytes because each int is 4 bytes, and we're allocating space for 50 ints on the stack. So that's what I want you to get out of this, right? Now, when we go back to this header, we see a bunch of structs. And this is all of the members. So in our example here, the members were age, name, and height in inches. In the executable header, the struct is called image DOS header, and these are the members: MZ signature, used bytes in the last page, file size in pages, number of relocation items, on and on and on and on and on and on and on. And that's all in the image DOS header. And as you can see here, as I'm highlighting these different members, you can see up above, up here, that this awesome editor is actually highlighting the bytes that correspond to each one of these members. So what it's doing is it's showing you how the computer and the operating system makes sense of these seemingly random numbers inside this file. They're actually not random at all, because when the operating system loads the file, it knows that the first few bytes will be part of this image DOS header, and it knows the size of every single one of these members. So it can therefore keep track of where every single byte is and what each byte represents, because it's told right down here exactly what each byte represents in each one of these structures. And it knows that once it's finished dealing with the image DOS header, that the DOS stub, which is this, will be next. As you can see, it's directly after it. And then it knows after that that the image NT headers will be next, and that will be made up of a PE signature, which is this famous PE right here, or bytes 5045. And then it knows that after that there will be a file header. And a file header will consist of the machine type, number of sections. So this is how machine code works. This is how the operating system and programs actually keep track of these bytes and are able to parse them and use them. They're not just a whole bunch of random numbers doing nothing. There is a structure and order to all of it. So for example, if you needed to get to size of optional header and you only knew where the beginning of the image file header was, what you would have to do is you would have to go down the number of bytes that make up the machine, the number of sections, time date stamp, pointer to symbol table, and then bam, you would be here to number of symbols. So we know the size of each one of these pieces of data in bytes. So for example, here we see this is 2 bytes. Here we see this is 2 more bytes. Here we see this is 4 bytes, as you see up there in the hex display. Here we see this is 4 more bytes. Here we see this is 4 more bytes. And then finally we're at what we were looking for. So the computer can count down what's called an offset. So if it's starting here at the beginning of the file header, which is right here at this 4C, then it knows I need to offset down by X number of bytes to get to number of symbols. So that's what it's doing in order to locate these different pieces of information. And that's all it does in the entire file, ultimately. Now, it has logic that it will do. It's not that simple. So, for example, let's say it gets here and this is not a valid number. Or let's say it tries to find this and it's not there, or something like that. The operating system loader has logic that will try to resolve some of those problems, or that will at least create some sort of exception or error so that it doesn't just crash the entire system or crash the program. However, that's the general idea of what it is doing. And interestingly, each one of these sections here, so we have something called the text section, the read-only data section, the data section, and the resource section. You can have other sections too. However, each section has its own section header in what's called the sections table. And each section header is a data structure. As you can see here, here's the name of the structure and the position in the section table that it's at, and then what it's actually called. In other words, which data that it represents is here in the value. So this is the text, read-only, regular data, and then resources. So the .text, sometimes called the .code section, is generally where a program stores all of its instructions. So it's assembly language stuff. It's actual code that a programmer wrote or that the compiler wrote will be stored in the text section. So that's a little bit of a clue right there, how the operating system loader and all the programs and software and the hardware even figure out which data in the file represents instructions versus which data in the file just represents information that the instructions will use and manipulate. So if it's in the text section, it knows that these are going to be instructions. to execute. So when the code starts, it's going to go into this text section. And, well, first the loader reads this header, because we're not actually in the text section. We're in the text section's header. And the loader will, and the operating system will see how big this section is. It will see where it starts, and it will learn some other information about it. And then when it comes time for the loader to transfer control of the program over to the program itself, to the code that the programmer wrote or the compiler wrote, the control will be transferred over to this text section. And this is where the disassembler works a lot of its magic. Disassembler has to figure out some of the other stuff too that isn't actually in the code section. It has to figure out where the data is and all that as well. But the disassembler's sort of main forte is going through this text or code section and making sense of these bytes. So it starts to look at these bytes in here, and it says, okay, what's FF25A420? What can that be interpreted as? And then what it will do is it will look up something like this. I'll show you right here. I'll put x86 opcode table. This is a pretty cool thing. I highly recommend taking a look at this if you haven't seen it. So this is a nice handy list of all x86 instructions and what they do. So for example, this is just, I'm just using this as an example. This may not actually start disassembling right at FF, because there's probably other things that have to happen up here before it actually hits the first instruction. However, what it would do is, let's say it wants to interpret what FF is. It will find it, and it will look up what that means. And see here, it can mean increment, it can mean decrement, depending on the context. And so it will start to actually make sense of all these instructions, because it knows that when it sees a certain instruction, the next two bytes after that instruction might be where it needs to grab the data for the operation, or for whatever instruction it needs, or something like that. So what it's basically doing is a disassembler is locating this code, and it is making sense of these bytes, and it's turning it back into what they call assembly language. And assembly language is just a nice way to write the instructions that these bytes correspond with in human readable form. So actually that page we were just looking at sort of does that. As you can see here, it's giving you little English instructions, sort of, or code that a human could actually read. So for example, MOV means move something from one place to another. SHL means shift left. SHR means shift right. And this SAR is shift arithmetic right. And so there's all these instructions. This is assembly language, x86 assembly language to be specific. So that's what the disassembler is doing, is it's going in here and figuring that out. And it creates what they call a disassembly. So let's take a look at that. Let's take a look at a disassembly. I'm at strings right now. I'm going to go back to the actual disassembly graph. So as you can see here, this program is called Binary Ninja. It's an awesome program. I highly recommend it. It's becoming a lot more popular for reverse engineering and disassembly. So here we see the address of the instruction, the actual bytes of the instruction itself. So in other words, 8B542428 were interpreted as move data from this area in memory right here, which happens to be the third argument to this function, into the EDX register, which is, as you know if you watch some of my other videos, it's a little slot inside the CPU itself to store data. So a disassembler has a quite enormous job of going through all those bytes that we see here in a hex editor and parsing them all into instructions. And in fact, Binary Ninja has its own hex editor that you can view by clicking Hex Editor. So that might also provide some more context for you. And in fact, I think there might even be a way to directly associate exactly which instructions, like this. Yeah, see, so when I have this highlighted right here, it's telling me exactly what it figured out this instruction was. So if I double click it, it'll take us there to whatever instruction corresponded with that hex code that we just saw in the hex editor. So in a nutshell, that's what a disassembler is doing. Now, there's a couple caveats to note about disassemblers, which you may or may not have heard. And one is that because it has to do that, it's basically making educated guesses. So the disassembly that a disassembler produces is probably not the exact code that was written and given to the that was written by the compiler or that was written by the assembly programmer. And it also could be different code in a higher level language as well. So for example, let's say I write a C program. Well, a C program runs through a compiler, and the compiler frankly changes it quite a bit. And then it tries to optimize things and cut things out. And then it writes assembly or machine code off of that. So if I want to go back from machine code up to the C, there are several different ways for every single machine code instruction that something could have been written in C. So when you decompile it back up to C, it won't be the same C as the person who wrote the original program wrote it in. It will be something similar, and it will perform maybe the same functionality, but it won't be the exact same code. And that's the same thing with assembly language as well. You can write things in assembly in many different ways, and so when a programmer writes something in assembly language, or a compiler does, and then it is assembled into machine code, it could be turned back into several different forms of assembly language, and it could do the same thing functionally and mean the same thing, but it might not be the exact same thing. And the other thing, too, is these disassemblers straight up make mistakes. So sometimes you'll go somewhere in the program, and there'll be like a whole bunch of data bytes because the disassembler never figured out that those bytes were instructions. I'm not really seeing that here, but that can happen, though, in both Binary Ninja and IdaPro and Hopper and any disassembler. So that's basically the lowdown on disassemblers and what is really happening. And it's a very important thing to understand the fundamentals of this, because when you are doing reverse engineering and disassembly and working with assembly and everything, you're working at such a low level that that type of knowledge will benefit you greatly, because you can start doing things like seeing byte patterns and writing cool Python scripts to process the byte patterns that you're seeing and make sense of them, and you can use them for malware analysis and reverse engineering and even exploit, finding vulnerabilities in programs and exploiting them and stuff. So that's all I got for you in this video, and thanks for watching. If you have any questions, post them in the comments. I'll put some related links in the description. Till next time.